All right, I will share my screen, rearrange. All right, perfect. So we have the last two chapters of this book this week. So um, in the past, we've talked through all of these different techniques, the different architectures, all kinds of understanding of deep learning, but we haven't necessarily answered the question like, why does this work or how does any of this happen? Um, so um, in this chapter, what we'll be digging into is like, how is this even possible? It seems kind of impossible that some of these things work. Um, so to start, the author was kind of walking us through um, mathematically, like why is this so unlikely? So they were showing that we have these data sets, and then we have architectures that are matched to them. And it's really surprising that actually we have so many parameters and so much data, and somehow it seems to work out so that the networks that we're training are always able to like fully fit these data sets, and they're so over parameterized that they could do really anything they wanted to, but still it seems like they come to some sort of reasonable conclusion and they can actually generalize to new data. Um, so one of the examples that they shared was AlexNet has 60 million parameters, but it only had a million input data points. And so it gets a little bit muddy because it had many different transformations of those initial images. So you could argue that you had more data than you had parameters, but in reality, it's just a bunch of variations of the same images that got passed to it. And then the other example that they shared was GPT-3 has 175 billion parameters, and it only had 300 billion tokens. And so the language model space, people have been doing all kinds of studying of the scaling of what is the correct size of the model, what is the correct size of the data, how much training should we do with this. Um, but in reality, people have been finding that these massive models are able to train, and typically you have more parameters than you do data points. Um, and it's surprising that we would want more parameters and data points because each of these parameters have many interactions, and then the actual number of like underlying linear regions and decisions that they can make is huge. It's some absurdly high number. Um, so one of the examples they were talking about is with the MNIST 1D data set that we looked in some of the previous weeks. If it had 40 inputs and each of those 40 inputs only had 10 possible values, that would still have 10 to the 40 possible combinations of all of those inputs. Um, and we only have, I forget what the data set size is, like 4,000 or something like that. It's not very big. So we have this massive number of possible combinations, not very much data to actually describe the entire space. And then we have these networks that are over parameterized, and then magically it all fits together, and we're still able to train something that gets a good result. It doesn't just memorize the values, it's actually able to um, learn kind of the true underlying pattern, and then it still works on brand new data. Um, and so one of the things that they were pointing out is that these models with this amount of parameters, um, we only have this very poorly defined like sampling of points in the space. And in theory, the model could do just about anything in between those points, but in general, it seems to find smooth spaces and find a generally good pattern. Because in theory, we've seen the graphs in the past chapters where it's like you have something overfitting, and then you've got 2 points, and instead of making the smooth line in between, it's just like all squiggly and going crazy. With these networks, it's theoretically possible for them to do whatever they want, but in reality, we tend to get reasonable solutions. Um, So one of the interesting experiments that they pointed out was that the network is still able to find some pattern and fit to this data even when we start just shuffling things and giving it random variations. So this graph is kind of interesting. It's showing here's how the model trains when we give it the original inputs and the true labels, and you can see that after some time, it's able to um, learn and it gets complete match of the data set. So it's able to completely learn the data set. And then alternately, if we do just random input, so we just give it noise on the input, and then we say, here, figure out um, some so the outputs again. So there is no pattern for it to learn. It's just got noise as input. And it's still able to learn the output, but it takes a bit longer for it to be able to figure out that pattern because there isn't really a pattern. Um, and then even slower than that, if we do random inputs and random labels, then you end up with this over here, where it's just learning random inputs, random outputs. So it takes kind of the worst case scenario where it's still able to learn this, but you can see it takes two or three times more training steps because there's not some simple pattern that it needs to unlock. It just needs to actually learn every point individually. Um, so the kind of one of the takeaways from that is we can look at that and we can say, well, maybe it's actually easier for these models to learn because we don't have that like mathematical chaos. We actually have some simple underlying pattern that the model is able to find. And I think that's generally true because you give a model a simpler problem to solve, it's able to find that more quickly than something that's very, very complicated. And worst case scenario is it's just random noise and it's not able to learn anything at all. Um, so there was some discussion about regularization, and they basically say we don't think that that's really what's causing this because we can train models with regularization, without regularization, and they're still able to converge. They're still able to come to um, decent solutions. So regularization helps us train better models, but it isn't necessarily the reason that we get convergence or not, or um, good performance. Um, so one of the things that they were talking about was the kind of spectrum of things that you can do in terms of when we're training these models, you can train an individual point at a time, or you can train a mini batch, or you can train the full batch. And so all of those kind of interact differently. Um, and one of the hypotheses is that you do that single point at a time. You're just learning from a single point at a time. You're introducing a lot of noise into the network in essence, because every individual point is pulling in its own direction. And so just the random shuffle of which order and all of that introduces a very, very noisy walk into your optimization steps. And so the belief that was that actually helps you break out of any saddle points or difficult points of convergence. Um, but what's been found is that we're still able to converge even when you're doing mini batch or full batch. You might end up with something that is slower to train or doesn't get as good of generalization, but in reality, it's another one of those things where it's like we've done the experiments and you can still converge with the full spectrum of things. So that's not the magic key to how all of this works. Um, I talked for a little bit about the over-parameterization, and so typically people have these networks that have way more parameters than we do data points. And one of the things that they kind of proposed is that this over-parameterization um, makes it so that there's many different sets of weights that can actually get you a good result. And so having a larger model, a larger set of weights allows you to have a bigger surface area. So if you have a very small model, there might be some specific set of weights that perfectly solves your problem, but it's very, very difficult for it to be found. It's difficult for the optimization to pass through exactly the right place to get to the final resting spot that then gets you the perfect loss. But if you have very, very high parameter count, then you're able to find one of the many solutions that lead to that similar path. And so that's kind of one of the hypotheses. I've generally found that to be true, where it's like more parameters doesn't necessarily guarantee that it's going to get you the best result, but it might get there faster and it might be easier to train, and you might not have to do as much work if you just say more parameters. Um, and so I kind of buy into that hypothesis that we need this many parameters just for the sake of finding the optimal weights. And then after it turns out that a lot of those weights are actually not particularly useful, and so they can be um, dropped later, or there's some other process that can be done to kind of distill them a little bit. So in this chart over here, they're showing the overparameterization factor. So this is how many parameters divided by the number of data points. So we can see that like this efficient net B7 is 50 times more parameters than it was data points. And we can see that it gets a very good top one error rate in comparison to everything. So there's different ranges of how over parameterized and how good they are. And so in general, we're trying to learn the networks that are good in terms of how many parameters, and then also good in terms of the actual scale and accuracy, because we could, in theory, just scale forever. That's kind of the LLM mode that a lot of people are in right now, is just let's take llama and make it bigger. Um, but in reality, we're also trying to find what are the optimizations in order to get more out of those parameters as well. Um, Talked for a bit about activation functions and how those have an impact. Depending on which activation function you choose, you can have different convergence patterns, and you can have difficulties in different regions. And they mentioned the initialization as well. So this is something that I kind of take for granted sometimes, because a lot of the deep learning libraries actually just will do it by default for you. So you say, here, I want a linear layer here, or I want a convolution here, and it will have a reasonable default for the initialization. But you have to be a little bit thoughtful on those. You can't just say, make it random noise of some random variance. Um, Actually has a big impact on how well they learn. So this is showing doing different scalings of the initialization, that you can get significantly worse values if you start at different places. Um, so as you have worse initialization, you have to do more training to kind of undo that bad initialization, and you can end up learning much slower. Um, So they also talked about the network depth, and this is kind of connected to that previous topic of when you have more parameters, you have more chances at a good outcome, basically. So if you do more layers, then you have more opportunity to get that needle in the haystack, because you can map all of these complex interactions, and some of the neurons can actually be dead and not doing anything, and some of the layers can not be particularly useful, but they might add some small amount. And so the way they're saying it is they're saying that you can actually have a bunch of subnetworks inside of these deep networks. Um, and that can be what drives the majority of the performance, but you need them to be deep in order to find the various different subnetworks. You can't just train them individually and get that same outcome. Um, So one of the things that they were talking through was the way these networks are set up, you can actually have many different variations of weights that yields exactly the same result. And so that kind of works in our favor because certain things just you can be within a range and it's actually equivalent. So if something hits a ReLU, it might just get set to zero anyway, so it doesn't actually matter how negative or how positive it is. Um, so you can end up with these equivalent networks where it's actually could mathematically not be the same, but in practice their output will be identical. And so that means that we have actually certain ranges of parameters that are completely identical networks practically. Um, and so there's many different ways in terms of activation functions or batch norm. We can end up with kind of rotations of the same network that yields the same result, but isn't actually the same. And so that kind of helps us a little bit in terms of um, we don't have to get the one exact true solution. There's actually um, ranges of possible outcomes that can be very good. Um, So one of the things that they were mentioning is there's this relationship between batch size and learning rate. So as you scale the batch size, you're probably taking less steps. And so you can also scale up the learning rate. And what has been found is that increasing um, the learning rate proportionally actually ends up getting you a better result. So on this side, we have um, batch size over learning rate, very small value, and it ends up getting the best result when you have a very small value here. Um, and as you go bigger, probably increasing your batch size more than anything, you end up getting worse error, and by large margins sometimes. I kind of question this a little bit because I feel like you should be able to do better than 40% um, test error, but maybe just not trained fully to convergence, maybe just comparing similar number of steps or something like that.
Hey, can I make a comment about that, Ryan?
Yeah.
So we were actually talking about this at work this week, and so what I was pointing out is there's a little bit of a tension because generally speaking, it's easier to get it to converge with a large batch size, but you're just not necessarily going to get as good of a final uh, error, you know. So if you take it to the extreme, if you say smaller batch size is better, then why don't we just always train on batch size one, whatever, right? And that would be full SGD. And for simple problems, it'll work. But like, you know, for some other things like whatever clip or whatever, it may actually just wander around for way too long and not converge in your lifetime or something like that. So
Yeah.
Question.
so the desire for small batch sizes and the desire for large batch sizes are a little bit like in tension with each other.
Yeah, go ahead, Andrew.
Is there any evidence that you could start with a large batch size and then switch to a small batch size to sort of converge to the lower, um, to the better model at the end?
In theory, you could. Um, one of so Jan LeCun from Meta, he had a tweet thread a while ago, and he was basically saying that in the ideal scenario, you would always just want to use batch size of one, actually. And the only reason that we don't is because of hardware constraints, because it's faster to say, let's scale up and do a batch size of 2 million. And then we can train much faster because we can do everything in parallel if we did everything one by one. Um, So that's another avenue of that, is like the actual hardware consideration of like, yeah, it might be great if we train with batch size of 1 and we get the best result possible, but in practice, like if we want to rip through 2 billion images, it's going to take so much longer if we just do one by one. But there was a paper that was doing the opposite of what you're saying. I don't know if I've seen anything do in that direction, but there was a paper that was basically saying don't reduce your learning rate as you train, increase your batch size. And that was a successful paper. So they were able to get good results by doing kind of the opposite, saying we start with a small batch size, small learning rate, and then as we go further and further into training, we increase the batch size. So I haven't seen the opposite direction. I haven't seen start with big batch and then go to small, but I'm sure someone at some point has tried it.
I guess the concern would be you might not escape the region with a small learning rate at the end, right? But
Yeah,
Yeah.
I mean, the general gist is you want to like find the right local minimum. And for that, you want small batch size or high learning rate or momentum or whatever. And then once you're in the right local minimum at the very, very end, so this would tend to be very small proportion of training. It's not like half or quarter, right? It'd be like the very, very end. Then you want to potentially do things like increase your batch size, just so that you're getting to the very center of the bottom instead of just close to the bottom.
hmm.
So small learning rate, large batch size, they would tend to help you, when you're taking steps, not step past the bottom, right? To only just walk a little bit by little bit to get to the actual bottom.
Thank you.
Some questions in the text. Um, on the haystack of needles versus haystack of haystacks thing, I think it boils down to what I was saying a second ago in terms of if you have a small network, there might be some very specific solution that if you get the right parameters, it will do exactly what you want. But in reality, if you take the bigger network and you have those properties that I was just talking about with the ReLU and the batch norm, you have many different ranges where you can get a good solution. And it does increase your overall search space. You probably have a bigger haystack now. But just the fact that you're looking for a million things instead of only one now, even though your overall pile is bigger, it still makes it easier to find one of the valid solutions, or at least close to it.
Yeah, to my mind, this is Sonali. I asked the question. To my mind, it sounds like somehow the it has to be a bigger portion, right, of the overall parameter space. All we are saying here is we are increasing the parameter space and we are increasing the space that is the optimal or the close enough to the minimum. But if we are increasing both, it doesn't automatically follow that it should be easier to find it. Somehow it has to be increased in a way that the minimum area is getting much bigger than the overall parameter space, or else the way we are exploring to find the minimum is more likely to get us to the minimum. There has to be something else.
Yeah, I mean, I'll chime in. I kind of agree
Yeah.
with that. So if you say in a small model, there's 10 to the 10 possibilities and there's only one good one. So the one good one is 1 out of 10 to the 10, right? If you say there's 10 to the 5th possibilities out of 10 to the 15, it's still a ratio of 1 to 10 to the 10. So I get what you're saying. Like, yes, I don't think that this is the primary explanation. I think something more like the stuff it was talking about like mode connectivity, and like how you're able to work your way to a good local minimum, or some of the stuff I think it's in later sections about how as networks get deeper, the majority of local minima are very close to the global minimum. You know, those kinds of phenomena I think make more sense than just simply how many needles are there, because to your point, if the size of the haystack grows proportional to the number of your needles, it's haven't really necessarily gotten any better.
Thanks, Ted.
Yeah, thanks for the questions. There's one more, but I think it's duplicate of what we just talked about in terms of changing batch size as you train. So talking about the training algorithms, SGD and Atom, and some of the parameters there, in reality, they were kind of saying SGD on paper should get you a better result, but Atom with the right parameters ends up getting you roughly equivalent and typically converges faster. So SGD isn't the magic sauce either. So one of the things that they were pointing out is that typically you get better generalization if the minimum that you fall into is flatter. So you might have some minimum that you fall into and is very, very sharp, and that can be dangerous because in reality, if you move in any direction, you end up getting a bad result. And so people have kind of analyzed these and they figured out that you really want the flattest one possible, because any variation doesn't really move your result a whole lot. It means that whatever has happened with your loss surface is well generalized, when you can measure that and you can actually see that it's quite flat. So talking a little bit about the architecture, they kind of point out later on that a lot of these architectures that we have might just kind of implicitly have a good structure for the kinds of things that we're doing. So if you have a CNN or a transformer, it's the case that they're operating in a certain way that is just aligned for vision or is aligned for text, and it is you can even get good results out of something that isn't trained. So they're able to kind of just say randomly initialize, oh, interesting, you can kind of do something with CNNs even if they're randomly initialized, and then we just tweak them in the smallest way possible. We don't actually learn the filters. So one of the interesting phenomenons with these networks is grokking. So this idea that you train a model and it's got a training loss that is zero. It perfectly fits your training data, and then you continue training it for an extra 1,000 steps or something, and then magically the validation loss was at some value and all of a sudden it drops. And it doesn't quite make sense because you're like, my model already perfectly represented my training data. But kind of the idea here is that probably somewhere along your sampling and training of additional data with different samples, you're kind of slowly smoothing things out, and you're making that minima flatter. And then once you kind of get it flattened out in exactly the right way, it's able to hit that point of generalization where before it was just memorizing your points, and then after that it's kind of smoothed the surface between and it can actually generalize to new points. So one of the interesting things about these neural networks is that they're pretty fragile if you know how to attack them. So Goodfellow a while ago figured out a way to do a sort of adversarial attack where you take an image and you say, pass it to a model, and then you figure out how do I perturb this image in order to make it get a different outcome. So you originally had a dog and you want the model to say plain for it. and you say, how do I modify this image of a dog in the slightest way possible in order to trick the model to say plane or something like that. And so we can see these examples over here where you're really putting the slightest noise on it. Like it's, even if I zoom in on this, like we cannot perceive a whole lot of difference here. But it will completely trick the model into making some other distinction. So just this small perturbation has convinced the model that this is an ostrich and this is also an ostrich. So it's pretty interesting. This kind of exposes that the models have learned something, but it's not the same that humans have learned, and it's also quite brittle if we can kind of just say shift these few pixels around a little bit, increase this intensity, decrease that intensity, and then you're able to get a outcome that is completely different, even though it's kind of imperceivable to us.
I think this kind of phenomenon makes it all the more surprising that it works. Like what you said, like it clearly didn't learn what we learn. It's not generalizing in the most general way, and yet, for all practical purposes, it generalizes just fine. Like,
Yeah,
that's crazy.
yeah. So we've talked a little bit about the over parameterization, and so you have all of these parameters. How many of them are actually needed? And so people have figured out that you can take these giant models and then you can actually just throw away many of the weights. You can set them to zero or just discard them entirely. Um, and so this pruning process, people have done some studying and they've figured out some smart techniques to say how do we ditch some of these weights. And so, for example, they were able to take the VGG vision network and they were able to eliminate all of the very low intensity weights and then reduce that to only 8% of the weights remained. And they still got decent performance. And you can go even further than that if you are okay with a little bit of performance loss. So it's kind of insane that we have this huge network, and then when we look at what is actually functionally driving most of the performance is a very, very small kind of submodel inside of it that is the useful central part. So some other researchers figured out that they could do this process iteratively. So they train a model and then they prune the weights and then they retrain only the remaining weights and then they prune that again. And they figured out they could do that a few times and they were able to eliminate 98.5% of the weights. So only 1.5% remained and they still were able to get good performance out of that. So it shows to what level we're actually over parameterized. Like we need this huge model to find the answer, but then the actual subset of that is needed to do that operation is much, much smaller. So people talk about GPT-4 being a trillion plus parameters. It might actually be the case that there is some perfect 100 million parameter model that can do just as well. We just don't know how to set the parameters correctly in order to do that. Yeah, Andrew, question?
Yeah, this would seem to have some relationship to adversarial training of some form, wouldn't it? I mean, in the sense that you want to help the model forget irrelevant stuff. And I mean, I'm just making lay comments here. I'm not anywhere close to as advanced as you guys are on this topic yet. But
I'm I'm not sure the interaction between pruning and being robust to those attacks. I think part of the problem with the attacks is like it's very confusing to us, but like this is the pattern that the model learned. And so maybe pruning the model removes some of that excess noise and gets us a pure signal of like this is what the model actually needs to know. But it's kind of unclear. I'm not sure exactly what the interaction between them would be. It could be the case that pruning removes stuff like this and makes it more robust, but it could also be the opposite. It could be that pruning only leaves whatever trace stuff is behind and actually important to the model. It could go both the directions. I'm not entirely sure.
Right. I might have used the wrong terminology. I think I meant more in terms of perhaps the terminology is contrastive learning, or cases where um, you have a component of the loss which is adversarial to the. I'll stop talking. Thank you.
The contrastive methods can there's a lot of different techniques that can contribute to the robustness. The general stuff that I've seen though, I follow some of the people that are doing kind of security related attacks on these networks has been that they're very, very fragile regardless of what you do though. There was
Gotcha.
kind of joke paper that popped up recently because some people had claimed that they had this amazing adversarial defense, and then someone came back with a correction of their paper basically saying I broke your defense with one line of code. So that's not necessarily the area that I focus on, but my general impression has been like people are trying to make these systems more robust and not have that artifact that we just saw. But I think it's very, very difficult because we don't have much control on the underlying, like what the model is actually learning.
Thank you.
Yeah, and I mean, if I can throw in another example, so so what we saw is an example where you're allowed to modify all the pixels, but what you want to do is you want to modify them a little bit so that to a human it's imperceptible. Um, there's another form of attack where people said, hey, if I only let you modify a very small number of pixels, I don't remember, it's like 3, 5, some very small number of pixels, but now you're allowed to modify them as much as you want. So you might have this very odd, bright blue dot in the middle of like the brown fur of a dog or something like that, right? Then like, can you get it to switch from like dog to ostrich? Like how few? And people were able to do it with like very, very few. So so the problem really is that in this high dimensional space, like, there's a few different directions you can move from any one point and example and still be a dog, but there's just gazillions of orders of magnitude of directions you can move that's not dog. And so you can have like contrastive examples, but in fact, in contrastive learning, generally what people find is that the contrastive signal is very weak because you're not really getting a strong representation of all the directions that aren't also dog. You're just getting a few hundred or a few thousand, and it's 10 to the whatever directions that are not dog. So I think in principle, what you're saying would help, but the problem is that you can't really provide enough coverage of the contrastive directions to make the model super robust.
Yeah, yeah, good point. Um, so pruning is one approach to kind of get rid of some weights, and another way that people have figured out works well is knowledge distillation. So in this approach, what you do is you train some large model, and then you say, this is great, it does amazing accuracy, but I want it to be smaller, I want it to run faster. Many different reasons you might want to do knowledge distillation. Um, uh, And so what you do is then you take a smaller model and you just say, okay, this model, you learn to just mimic the other model. You just see the same input. I want you to get the same output as this other larger model. And this is shown to be and sometimes a better teacher than the raw labels themselves. So you train a model just on the individual labels for this is a cat, this is a dog, this is a car, for example. And then on the second stage, you train your model to match the probabilities. And so that actually gives you a much more granular signal than before you just got a single classification saying if it was this thing or that thing. And now that new model is actually giving you probabilities saying, I think it's this percent car and this percent dog and this percent cat, and having that granularity of you actually have 1,000 different outputs for your whole ImageNet model. Turns out that that gives you a very, very strong outcome. The second one doesn't have to be a regression model. It just depends on what your task was. It can be a classification model still. It can be regression. It could be you could distill GPT-4 if you set things up correctly. So it doesn't uh, depend on a specific regression or classification or anything. You can kind of distill any model if you just kind of match the output scheme. I think that's maybe I jump to the next chapter really quick. I already mentioned this, so this is the stuff on CNNs and transformers, probably actually very good even out of the box. Running out of time, so I'll just push us to the next chapter. So the next chapter was all focused on the ethics side of things, and so I think this is a big topic for a lot of people lately, especially with GPT-4 becoming kind of prevalent in everything. And we've got the diffusion models that are generating images of stolen art and stuff like that. So this is probably more relevant than even when the book started. So one of the things that they touch on is just value alignment and how we get to that point. How do we define it and what kind of failures we have there. So in terms of value alignment, kind of the overarching goal is we want these models to do what we want, and we want it to kind of have our values, but that's a very murky and gray area where all of us might actually have different values that clash in various different ways. And so one piece of this, one piece of it is how do you actually kind of encode that into a model? And so one of the interesting things that they mentioned was some people have tried to tackle this by just kind of laying out some rules. So they say, do this, don't do that, do this other thing. And then the alternate approach was actually kind of taking a polling of people and saying, like, if anyone's played like the trolley problem game, it gives you a bunch of scenarios and says, take this or take that. And just polling a bunch of people, you can figure out what the general taste is for different decisions. And that's obviously still a flawed way of representing things, but it is a way to get some kind of codified representation of what people's values are and how to get that inside of a system. So one of the big topics is bias. So you don't want your models to be biased and cause certain things to happen. It's kind of difficult to define. Some models have more direct kind of ethical impacts and others not quite as cleanly, but if you're hiring job candidates, you don't want to make a decision purely based on gender, and so that can seem obvious. You might say, okay, I'm going to make a model and I'm not going to include the gender feature inside of my model, but you can actually end up falling into a trap where a bunch of your other features might very easily uncover that. So if you're also looking at name, if you're looking at job history, if you're looking at colleges, they might have gone to a women's only college or something like that. There's a bunch of different things that can derive back the original feature that you were trying to hide from your model. So doing that process of just kind of saying, I'm going to make my model blind to it, isn't a valid strategy. So you have to kind of, after the fact, still measure your model and understand how it interacts to those sorts of things. Make sure that it's not biased. They have a lot of good examples of this. So even Gemini recently fell into this trap. So they trained a model. On one of the data sets, and that data set turned out to just be a whole bunch of white celebrities. And then people went to it and they asked, hey, make us Obama. And then it just goes and it makes him white. And so if you don't have that representation in your data set, then you're going to end up with a model that also doesn't know how to represent it, and it's going to get you outcomes that you don't want. So Gemini more recently, similar example to that, people were saying generate something, and it was just turning everyone into people of color, and people weren't very happy of that in the opposite direction. So one of the extra layers of complication with this is the intersectionality. So if you have multiple different marginalized groups, you might be taking your data and going, okay, I need to be careful of people of color, and I need to be careful of women, I need to be careful of everything else. And then you might take some safety measures in order to try and balance that, but then you aren't able to correctly kind of rectify the combinations of groups. And so that can become very difficult and tricky because it's managing multiple different layers of related things at that point. So this is what I was mentioning earlier. They're calling it fairness through unawareness. So even if you have your feature that's hidden, it still might come out somewhere through your data. Here's what I was mentioning earlier in terms of like the famous Asimov's 3 laws of robotics. So that's one method. You can go top down and say, here's the rules, now enact those rules. But there might be plenty of different ways that those rules can then be abused and gamed in different ways, so you don't actually get the outcome that you truly want. And then on the flip side, you can have a bottom up where you say, okay, I'm going to poll everyone about a bunch of these decisions. How do we actually manage these? And those are not quite perfect either. So they talked a bit about the transparency, and so I hadn't really taken a view at transparency because people always go basically directly to explainability. But transparency is just this idea that you have any vision on the details of the model. So do you know what architecture it was? Do you know what data it was? Do you know what training procedure it was run on? Do you know all of those details? So transparency is good because you want to know what the model is, what went into it. But most people go almost directly to explainability because they want to say, okay, I'm using this model. Why is it making this specific decision? So levels beyond transparency, explainability and interpretability. So we've talked in the past, we've gone through some explainability content. So we've looked at Lime and Shapley and stuff like that. And these are techniques that allow you to um, look at your model and kind of say, okay, what is the relationship here? If this value was a little bit higher, what would it do? If it was a little bit lower, what would it do? And so these are kind of post-training techniques that you can use to then get something that's a bit more interpretable out. In practice, I'm still not huge fans of those techniques. I've never had it really inform any decisions for me. A lot of the time, um, you look at the results and it says, okay, this made it plus 60% and this made it minus 20%. And what do I really do with that information? Sometimes it's interesting to look at, but I haven't particularly had a situation where the Lime or the Shat values changed what I was intending on doing.
Yeah, I think your use cases tend not to be like the ones, where it's like uh for, if a loan's denied, right, then it's like for people very similar to you, what one or two things would make the biggest difference into turning it to a yes, right? Or if it's making a recommendation, don't do the surgery, what one or two things for somebody, you can't change their age, you can't whatever, but like what. So then maybe if it said, well, actually, if you lost a bunch of weight, then I might actually say that you're safe to have the surgery, then the patient might try and lose some weight or something like that.
Yeah.
But yeah, it is pretty limited. They're not global explanations. Not like linear regression, you can have a nice, clean global explanation.
Yeah. One of the applications that they mention that is problematic is facial recognition. So this has been a problem for many different reasons, partially because it's more performant on certain subgroups, but also because a lot of the groups that are doing this sort of facial recognition stuff are overextending what they claim it can do. So they're claiming that they can just detect criminals from their face and a bunch of other stuff that they can't really accurately do. So there's a bunch of dangers with that. There's also the point of surveillance and tracking people, and so there's definite debate on whether that technology should even be used at all. So one of the other levels is the militarization. So great technology that can very accurately detect things and help with tons of military applications. Just something that has to be dealt with carefully because there's actual life and death scenarios there. So um, the implications are broad on that. So many different good and bad things that can come from that. Um, Another section they talk about is the fraud. So I'm sure that with ChatGPT and everything, all of the spammers and scammers have significantly skilled up in terms of better English, better convincing skills, better scalability. They can just say, now I have 1,000 chatbots that are just trying to convince people to give their credit card and stuff like that. So that's another one of those areas where I'm sure fraud will be a difficult problem in the future when we can kind of just infinitely scale that stuff and we have to defend against it. And it's very difficult to tell the difference between spam and genuine content and if you're actually talking to someone. Um, Another important area is data privacy. So if you didn't agree for your data to be trained against, then it shouldn't be trained against. A while ago, we were looking at a competition actually where we were trying to do an unlearning process. So you have a model, it's been trained against some data, and now you're trying to remove the influence of that data. So you can't detect that that data was trained against initially, because that's one of the kind of interesting privacy concerns is you might be able to extract out someone's data from just the model. So if you trained against someone's medical records or something, it would be bad if you could then take that model and say, okay, give me that person's medical record back. You don't want that leaking out. So it might be a great model that's able to help people with their diagnosis and stuff, but it's able to leak people's whole medical records out. That's probably not something that people want. Um, so data privacy in these networks is pretty complicated, because you don't know exactly what can be coaxed out of these models sometimes. Um, intellectual property also very difficult. People have kind of taken the approach that anything that's up on the internet is fair game, and so we've ended up with these interesting scenarios where people have just scraped all the text, scraped all the images, pulled from licensed sources, and taken people's artwork and all kinds of stuff like that. So we have all of these models now that are of questionable origin, and now there's a bunch of battles on should these models even be allowed, and then um, how do we prevent more people from doing that in the future? One of the interesting things that they pointed out in here was this idea of moral descaling and automation bias. So this idea that as we get things more automated and the AI might take some decisions away from us, we might lose some of our moral abilities because we don't have to make those kinds of decisions as often. I don't know if I entirely buy into that, but I also don't know exactly what the future is going to look like and what people's day-to-day life will be. So I thought that was an interesting point, though. The environmental impact is something that people have been digging into a lot lately. So understanding, we trained GPT-4, it took 10,000 GPUs for a month. How much energy did that actually take? And so the question is like, is this actually what we want to be spending energy on? What is the environmental impact? Is there something better we should be doing with this energy, or should we just not be spending this energy at all? Are we actually getting the positive outcome that exceeds the environmental impact? And so if you go through and you read some of Meta's reports, a lot of their stuff is actually talking about the environmental impact and how they've offset all of their um, CO2 and electricity and all of that stuff. Um, so whether or not you can truly neutralize that is unclear, but some of the companies are trying to make an impact in that direction. Um, Big societal impacts. So we get these amazing models, we get better and better at automating things. There can be big impact on unemployment. So if not everyone needs to work anymore, maybe that's good, maybe that's bad, but it will have a social impact, and we'll have to see what actually happens in the end. Um, so one of the problems with this is the concentration of power. So we've already kind of seen this happen, that um, more and more of the top stuff is going through OpenAI and Meta and Amazon, and all of these companies are just getting stronger and stronger because they have the compute in order to generate these models. And then even the small research universities aren't able to keep up. They just don't have a data center with 10,000 GPUs sitting around for students to play with. So then their research kind of gets dwarfed by these companies that can throw massive resources to things. So everything kind of flowing up to them. I think that's it for the chapter. Any questions in the chat?
So Ryan, maybe we can close with if people are interested in this, any recommendations where people might want to go and look. I was thinking Luther is probably a good organization to look up if you're interested in these kinds of topics.
Yeah. Yeah. Faye, you have a question?
Yes, I have a question. You mentioned about the student model and about the teacher model, and I was thinking about it, that the challenge here is to balance the pruning of the teacher model, so it can have a mm, it can it can still retain the sufficient capabilities for the transferring the knowledge, because the problem is we will lose the significant information, and we will see a significant accuracy. What do you think about we can use the model pruning or knowledge distillations that you mentioned to create a fast, accurate model for the fraud detections that you were talking about?
I think it's the distillation and the pruning generally works well. Like that's been proven to be, you can take a larger model and you can make it smaller, and generally you can get a outcome that is nearly as good with, you can make a model 10 times smaller that might be 1% less accuracy. Whether or not it can handle fraud well, I think is a bit unclear. I think that will just be as good as the model basically was to start.
Or just maybe use the fine tuning for the student model uh, on the fraud detection task.
Yeah, yeah.
So in that way, we can optimize the performance and make sure about the accuracy.
Yeah, yeah, you would want to do some amount of retraining.
Yeah, because the problem is just not to lose the information during this process.
Yeah.
Right, thank you.
Yeah. Thanks for the question. Yeah, Andrew.
So I'll be reading this book. I mean, I found your group only recently. I'll be reading this book sometime in the future. Did it cover issues? I'm rather interested in issues of destructive, learning during fine tuning, and also the broader topic of how we might find ways to cause models to forget information, which seems to be a topic that's not well understood. By the way, am I right in stating that?
Yeah, that's an area people are very interested in. So there's kind of two sides of that to we have these huge models. How do we inject a new fact into them? And then the flip side is how do we make it forget something? And I think it's an area of big interest, but I don't think anyone's gotten anything too convincing yet. I saw something, I don't know how to say their name, Lamini. They did
Yeah, yeah,
some
yeah.
memory tuning thing that I thought was interesting, but I haven't dug into it too much yet.
Yeah, there was a paper that just came out, I think this morning, or at least that's when I saw the news of it. I have the link if you'd like me to post it in the chat.
Yeah, yeah, that'd be cool.
Uh, but does
But
the
in
book cover the destructive learning issue?
not really. So we didn't really touch on anything like that in the book, no.
Thank you.
Yep. I saw you commented about talking about future plans, Ted.
Sorry, let me wrap the recording here.